are some sense highly correlated proteins, and the ones that aren't connected in some sense are not correlated. And the idea is to look at this structure, and maybe that suggests certain, or a way to test certain scientific hypotheses. And so it might be an exploratory tool, or it might be a way to check out certain hypotheses. It might be a data reduction technique. It might be some way to, as a first part of an analysis for something else, and so on. So there's many different places and different ways that these graphs could be used. Usually, the difference between a network and a graph, and this is not always true anymore, but it used to be the following thing. If the nodes are individuals, it's a network, and if the nodes are features, it's a graph. Okay? And again, not everybody follows that. Let me explain that statement a little bit more clearly. Imagine we take our data. So let's suppose I have n observations. So I'm going to think of these as x1 to xn are drawn from some p. Let's say that these are cells. Each observation is a cell. And then on each cell, I measure a bunch of genes or proteins or something like that. So these are the features, 1 to d. And, or if you want, these are people, and these are features we've measured on the people. And usually, I use the phrase network to mean the nodes are like this. For example, Facebook. If I put a node for each person, and then you put a line between anybody who are friends, that's a network. At least that's the terminology I'll use. But if I'm interested in how are these genes related, how are the features related, which features are correlated, highly correlated with other features, that's a graph. Okay, so at least that's the terminology I'll use, and it's, I would say, most commonly used that way, but there are people who will use them interchangeably. So just so you know, I'm talking about the relationship between the features, not the people. All right? And so that's the kind of graphs we want to talk about. Now graphical models, which we're talking about some graph that's related to some probability distribution in some way. There are many, many, many different types of graphs. Okay? And the most common ones are directed. In fact, directed acyclic graphs, DAGs, and undirected. There's a whole industry of people creating more general graphs, things that are in between these two things that involve double lines, triple lines, arrows, non-arrows, and so there's a large, large, large literature. But I would say the most commonly used ones and the most useful ones are directed graphs, which means something like this, and undirected graphs, which, as the name implies, doesn't have arrows. That's the big difference. And these you took in 701. And remember what it means. It just means that the distribution factorizes. So it's p of x, then it's p of y given x, and then it's p of z given, and the only parent it has is y. So in this case, it would be p of z given y. So this is how that directed graph implies that you factorize the distribution. If I had had another arrow from x to z, then this last term would be p of z given x and y. Okay, so it's just a prescription for how you factorize the distribution. And it's important to realize that when you write down a graph, you're not writing down a probability distribution, you're writing down a family of distributions. So this directed graph refers to all distributions on x, y, and z that can be factorized this way. Right? But we're not going to study directed graphs. We can later if you want, but I think you've seen, again, this in 701. I think undirected graphs, from my opinion, are much more useful. And of course, the difference here is there's no arrows, and we have to talk about what this means, and it can mean many different things. There's more than one way to define these undirected graphs. The key is, though, that there are nodes, and again, these are supposed to be not people, but features. Right? This is 3 different features measured on every person. And then there's going to be either an edge between two things or not. So the graph consists of 2 things. It consists of the vertices and the edges. So in this case, the vertex set is x, y, z. And the edge set can be represented in many different ways. I could represent it as a set of pairs. So I could write it as, well, there's an edge between x and y, there's an edge between y and z, and there's an edge between, well, that's it, right? That's just two. Or you can think of it as an adjacency matrix. You can think of E as a matrix. The diagonal is sort of arbitrary. We can make them 1 or 0 by definition. It doesn't matter. But what matters is that x and y are connected, so there's a 1 there. X and z are not connected, so there's a 0 there. And then y and z are connected, so there's a 1 there, and so on. Just tell that's the adjacency or edge matrix. And again, the diagonal in this thing is arbitrary. So that's all there is to it. There's just this set of nodes or vertices, and some things are connected and some things aren't. And the question is, how do you interpret these things? And the more difficult question is, how do you estimate them? So I like to say there's 3 flavors of graphs. All right, what I'm going to call, first of all, marginal or correlation graphs or association graphs. And these are the easiest to estimate. So we're going to start with these graphs. Then there's partial correlation graphs. These are harder to estimate. And then finally, there's the ones that are probably the most common, which are conditional independence graphs. And these are the most difficult of the 3 to estimate. So we're going in order of how hard they are to estimate well. And they're all useful. They just have different interpretations. So it's just critical that we know which one we're doing and that we understand how to interpret it. And depending on the field, it depends also. In each field, some of these are more popular than in other fields and so on. OK. We scared that person away. All right. OK, any questions before we start? So, yes?
So, in general, are there no, so I guess in the independence case, we have interpretation of undirected loops, one loop, so the same variable. But are there cases where there is an interpretation of loops, single variables, and other?
Yeah. You can anything you can think of to do to this graph, somebody has written a paper about it and come up with an interpretation. Like putting self loops. In these graphs, these are supposed to have no cycles, acyclic, but you can have cycles and so on. But then it becomes a question of how do you interpret it? And and generally speaking, people will make up interpretations and then try to prove that the interpretation is consistent, it has a consistent interpretation and so on. They get very complicated. Things with some directed and some undirected. Some people will have two lines, And then the art there is to come up with some mathematical, well-defined definition and show that it has a good interpretation and so on. We're going to just stick, though, with just the simplest, which is just there's either an edge or there isn't. Any other questions? All right, so let's start with these correlation graphs. And so I'm going to write a typical observation now. It has D features, so I'm going to write this as okay. So this is one person's observation. The round brackets indicate feature 1, feature 2, up to feature D. So this is a vector in RD. And between any feature, we're going to define some notion of correlation or association, which I'll write probably just as that I use R, JK. Sorry, rho JK. So what we want here is some notion of how correlated or how associated are these two features, J and K. Again, we're not talking about people, right? We're talking about features. So it's like how correlated are height and weight, or how correlated are gene 5 and gene 18, or something like that. And what we're going to typically do is estimate this on each pair, and then we're going to make a decision on whether to connect them or not. And there's 2 ways you can do it. You could just say, if this is 0, don't connect them. If it's not 0, connect them. Or more generally, you could have a threshold. You could say if this is bigger than some epsilon, you connect them. Otherwise, you don't connect them. And that threshold might be 0, or it might be some other number. Okay. Now, I want to distinguish, though, different measures of association between random variables. So, at the very least, one more piece of notation before we continue, actually. I'm going to use this notation, which is pretty standard. This means x and y are independent. That's just short for x and y are independent, right? So that just means p of x, y is p of x times p of y. And also, we'll be writing x is independent of y given z. That means when we condition on z, x and y are independent. So that means what? That means p of x and y given z factorizes p of x given z, p of y given z. So one property we want to have is that if x and y are independent, it should imply that this measure of dependence, whatever it is, should be 0. Anytime if they're independent, they should be uncorrelated in whatever sense we're measuring correlation. But many measures of independence only work in this one direction. Okay. Some, however, have a stronger property, so I'll call this a strong correlation, that x is independent of y if and only if this is not required. You can still get useful graphical information by just using weaker measures of correlation like this. This is going to give you more information, although these measures of information or correlation are going to be harder to estimate typically. Okay, but it's just important to realize that if we're using these ones, it doesn't mean it doesn't have the if and only if. Things can be uncorrelated without being independent. That's all I'm saying. So I thought I would make a kind of a chart here, which is on page 3, because I know there's a lot of different types of correlations we're going to look at. So this chart is actually pretty useful, I think. So I'm going to look at, there's so many measures of association that have arisen, in 100 years of statistics and so on. So I'm going to focus on what I think are really useful ones. I'm going to pick 2 old ones, which are sort of oldies but goldies, right? They've been around for a long time and they're still useful and they're simple. And then 2 newer ones, which are pretty interesting because they have different properties and people are still figuring out their properties. So the 2 oldies are the Pearson correlation, which I'm sure you've seen before, and the Kendall's tau, it's called. And the 2 newer ones are the distance correlation and what's called tau star. So we're going to look at 4 different measures of association. We can build a graph from any one of these 4. And now I want to list some of the properties. So the strong property, which means that if it's 0, it implies independence. These 2 don't have this property. They're not quite measuring. So they're measuring something weaker than independence. They're just measuring some sort of association. But these 2 have the full strong property. Okay, now I'm going to put down something called robust. And what I mean by robust is it's not sensitive to outliers if you get extreme observations. And on this one, Pearson fails. Kendall's tau does well. Distance correlation fails. Tau star does well.
What is outlier?
An outlier, an extreme observation. Then there's, I'll call this fast. This is a little bit tricky to put this down because it depends on how good you are at computing and how we compute them, right? So it's a little bit hard to say absolutely, but these are definitely, however you measure it, these are easy to compute, and these are more difficult to compute. I'm not saying they're impossible or really, really hard to compute, but there's definitely a division there in terms of the amount of computing. And now comes a really important one, which is a lot of the literature focuses on just testing, is this correlation 0 or not 0, but you'd actually like to have some measure of the size of the effect. We'd like a confidence interval for the size of the correlation. So do we know how to compute a confidence interval? And for these, yes, yes, yes. And this one, I'm going to put sort of, because this is largely an open question. I'm going to show you a way of computing a confidence interval, but it gives up a certain amount of information. So to some extent, as far as I know, this is still a bit of an open question, how to do this efficiently, statistically efficiently. In other words, I'm going to show you how to construct a confidence interval, but it's wider than it might need to be. Okay. There's also a big, big literature about using reproducing kernel Hilbert spaces to do all these things. But these are all just different versions of this. So I'm lumping that together, reproducing kernel Hilbert space. I'm thinking of this as basically being in the same category as this. And I'll give you examples of that when we get to it. So that's the big picture. That's what we're going to go through. Okay. There's been this revitalized interest in all of this measuring correlation in the last few years. So that's why I'm covering so many of these different things. There was also one, actually there was a paper in either Nature or Science by some people who created some new measure of correlation. You know, what prompted them to do this was they had experimental data that tended to be on the unit square, but tended to fall on small subsets of the unit square. And they wanted measures of correlation that picked that up. But they seemed to not know about the fact that there was like 100 years of work about these different types of correlations, as far as I could tell. I don't know. I'm not covering this one. Maybe that's unfair. I think they've written a recent paper which hasn't appeared yet where they try to compare it, though, to some of these more standard methods. So I'm not covering this one. I've even forgotten what it's called. Something about the word information is in there somewhere. Basically, they discretize the space and they measure the mutual information and they do something else, and there's some complicated thing. All right, let's start with the simplest one, though, which is Pearson's correlation, which is the one you would have learned in several places. So let's do this. Let's get a brush. Get through here. All right. I made it. Whew. All right. So the Pearson correlation, remember that between two random variables, let's put down the formal definition. It's the covariance between x and y divided by the standard deviation of x and the standard deviation of y. So I'm sure you've all seen this before, and you remember this. This is always between -1 and 1. And of course, this is very easy to estimate. We can estimate it with, let's call it rho hat, or some people will call it r, which is just the sample version of these things. So that would just be the sum of xi minus x bar, yi minus y bar, over the sample standard deviation of x and sample standard deviation of y. Okay. So the nice thing about Pearson's correlation is how simple this is and how quick this is. What are some disadvantages of this? Why might this not be a good thing to use? Yeah, it's really measuring some sort of notion of linear dependence, right? Because if the data look like this, you'll get a very strong correlation. But if the data look like this, they're clearly dependent, but the Pearson correlation will be 0. And so it's not, it's only picking up, this is this non-strong property. It's only picking up some aspect of the relationship. So it's going to miss certain types of dependence between these things. But let's go with it for now. And let's say we are going to use this. A natural thing to do is to maybe test. So now I'm concentrating here on this was just on 2 particular random variables. But remember now, I'm going to do this for all of my random variables, right? I have j equals 1, 2, up to d features. So for each pair of features now, I want to know, are they correlated or not in this sense? So I need to test many hypotheses. I want to test, say, that rho j k equals to 0 versus rho j k is not equal to 0. Any ideas how I might do that hypothesis test? So you're writing an exam now. I'm asking you to test this hypothesis. You're going to do what? And you're not, no, panicking and leaving the room isn't an option. You have to actually write down an answer. 7:05 hasn't been that long ago. Right, we'll form some test statistic, like a Wald test, say, and take the estimate divided by its standard error. Now, it turns out, however, that Fisher, whose name has come up quite a bit, realized a very interesting fact. This is a very old but useful fact. So it's true that by the central limit theorem, rho hat is approximately normal, and so we could construct we could construct rho hat minus 0 over some estimate of the standard error and use a z-test. But that depends on the accuracy of this, the accuracy of the normal approximation. And what Fisher realized, you can increase the accuracy by doing, well, what's now called the Fisher transform. So what people actually do, and if you're going to use this method, I recommend this is what you do. Let's put this up here, so we'll save this, is to do this Fisher transform. Which is defined as follows. Zjk is equal to 1/2 log of 1 plus, this is the sample correlation between the jk feature and what Fisher showed was that this satisfies the central limit theorem. This is approximately normal with some mean. This is what is theta jk? It's exactly this function applied to the correlation. So if I call this g of r, then theta jk is just g of the true correlation. And in particular, this is 0. It's easy to check. This is 0 if and only if the correlation is 0. So testing whether rho is 0 is the same as testing whether theta is 0. And the amazing thing about this, though, is not only is this a better normal approximation, but the variance is 1 over n minus 3. Very simple variance. Often when you think about it, like if you think about p hat, what's the variance of p hat when we're doing a proportion? It's p 1 minus p over n. Often the variance involves the parameter itself, right? This doesn't. There's no unknown parameters in here. That's called a variance stabilizing transformation. So this Fisher transform has this remarkable property that the variance is very simple. It's a better normal approximation. And now we can do our...
What do you mean by n minus 3? Why you put as 3?
Well, I'm just telling you that's a theorem.
But since you're right asymptotic formula, so what do you mean by that?
Oh, by putting it on the right-hand side, you mean?
Higher order?
Oh, no. So whenever I write, when we write theta hat is approximately normal, theta with, some mean, say some variance sigma of n. Technically what we mean, right, is root n theta hat minus theta converges in distribution to a normal. Right, so it's the same thing.
But minus 3, it does not make any sense.
It's just a more accurate approximation. I'm just saying if you actually can run an experiment, you'll see the variance is about 1 over n minus 3.
In what sense do you mean more accurate? You
Just
mean
practically.
higher order or some
Oh,
like that?
yeah, I don't know if it's technically a second order approximation, but yeah, I see what you're saying. What he's saying is asymptotically, n minus 3 and n are the same. There's no difference, right? But as a practical matter, and I don't know if it's second order correct or not to say this, but this is a good approximation to the variance. It's a good question whether it is actually, in some provable sense, that n minus 3 is somehow giving you a more accurate approximation, even asymptotically, than 1 over n. I suspect not. I suspect it's just a small sample phenomenon. Okay, so now we have a procedure, right? Because what we can do is, for every pair, we could reject the null hypothesis that we're testing over there if zjk is bigger than what? Well, you might say your first guess would be this. Right, that would be the test based on this thing. However, there's a bit of a problem because we're doing this for every pair of edges. So that creates what? That creates a multiple testing problem, right? Remember, if we test a whole bunch of hypotheses at, say, level 5%, doing one test at the 5% level means the chance you'll make a type 1 error, if the null is true, is 5%. But if I test 1,000 of these things, we're going to start making all kinds of type 1 errors. So there's various ways to correct for that. The easiest one is, remember we did the Bonferroni correction, where when you do multiple tests, instead of testing at level alpha, you test at level alpha divided by n, where n is the number of tests. That's a pretty harsh correction, but that's the easiest correction to do. So that means we should actually divide here by, let's say, capital N, where capital N is the number of tests we're doing, which is what? It's d choose 2. Did I include that in here? Yeah.
You can basically never reject it, though?
Well, it's going to, I wouldn't say you're never going to reject it. It's going to definitely reduce your power. And there might be better things you can do. We talked briefly about false discovery rates, for example, in 705. And so you could, instead of doing this correction, you could do a correction like FDR, which has much higher power and so on. So I'm just kind of putting down the simplest one, but you're right. We're going to definitely find many fewer edges if we do this, especially in a very big graph. So this might not be the best thing to do, but it is a way of doing it. So there you go. This is one way to do this. We can do this transform, do this test. We can also get confidence intervals, however, because if I use this approximation, what I'll get is zjk plus or minus the square root of alpha over, and whether we correct it or not, let's say we're doing it correctly. This is a confidence interval for this transform parameter. So if we undo the transformation, let's suppose we call this A and B. You apply the inverse transformation, which is e to the something plus e to the something. It's the one of those transcendental things that I'm forgetting. But you go G inverse of A and G inverse of B. You just apply the inverse transformation, and now you have a confidence interval for rho. So you construct it on the Fisher transform scale and just transform back. And you can do that for every pair if you want. And so we have a way of testing whether the correlations are 0. We have a way of getting confidence intervals for every correlation. It's all very simple. And again, there are different ways to construct the graph. You could construct the graph if the correlations are significantly different from 0, or if they're just bigger than some threshold you pick, epsilon. You have many different options for constructing the graph. So this is very fast, very simple, and hence very popular. Okay, one last thing though is, do we really have to rely on the asymptotic approximation to do the test? Is there any way to get an exact test? I mean a test where the p-value truly is the probability of falsely rejecting it truly is less than or equal to alpha without relying on asymptotics. I can see you're making the motion with your hand for a permutation. That's right. Remember the permutation test. You could just do a permutation test and get an exact test if you want. If the sample size is large, it won't make much of a difference. But if the sample size is small, it will make a difference. Let me remind you how it works. So pretend for the moment there was only 2 features. This would have to be, you have to do this, of course, for every feature. But let's suppose there was just 2 features here. So we have x1 to x and y1 to yn. We get our rho hat. Then the way the permutation test works is you randomly permute, doesn't matter which one, say the second one. Because under the null hypothesis that there's no correlation, the distribution won't change if you permute this. So I permute this, and I recompute the statistic, and I repeat that many times. So I get these. Let's say rho hat to rho n. And then the permutation p-value is just how often these permuted p-values, let's say an absolute value, are bigger than the observed one. Remember that? That's a non-parametric way of doing testing that doesn't require any asymptotic approximation. But it does involve a lot more computing, obviously. Okay, and that's another way to get a p-value from this test. It doesn't give you, permutation tests don't give you confidence intervals. They only give you a test for the null hypothesis. So whether you do the asymptotic approximation or the permutation method really depends on how accurate you want to be.
So if our data is, if it's 0 correlation but is not independent, does the permutation test give us anything extra?
No.
Or are we still constrained by the fact that we're looking at
Right, this is right. You're not getting anything extra out of it. This is right. That problem we're going to solve by doing other measures of correlation. Okay, so there you go. And a lot of graphs are constructed using basically just using Pearson correlations. So now we're ready to go on to the next one. Any questions, though, before we continue? All right, so the more, let's keep that up there. Because we've talked about the entire first row. I want to mention Kendall's tau. So Kendall's tau measures correlation or association, whatever we want to call this, in a different way. The dependence between x and y is measured by taking, what we imagine is, let's take 2 draws of the distribution. Just imagine getting 2 draws of the distribution, x1 and x2, and y1 and y2. So here's one. Well, let's do it this way, actually. Here's x1, x2. Here's y1 and y2. Just pretend for the moment you had 2 observations. Then we're going to look at x1 minus x2 and y1 minus y2. And we're looking at the sign. So in a sense, we're kind of throwing away information because we're only looking at the sign. This is going to be +1 or -1. But that's what makes it robust. If there's extreme observation, it doesn't have a big effect. And we're going to look at the mean of this thing. So I drew a little diagram here, which is intuitively what's going on is it's counting the concordance or discordance that if these are lined up this way, then these have the same sign, and so that's like a positive number there. But if they're lined up this way, that's called a discordant pair, and that makes that a negative. So what it's doing is it's in some sense averaging how much discordance and concordant pairs there are. This is a pair of observations. Remember that the fundamental rho xy, let's go back to rho, was defined by This was defined in terms of a generic random variable. Then we compute it for the sample. This is the same thing. This is for a generic pair of observations. We haven't gotten to the sample yet. This is a population definition of the parameter. You give me 2 random draws from the distribution, 1 and 2. That's the definition. So to estimate this from the sample, I just put the sample averages in here. So to estimate this from the data, what do I need to do? I need to use pairs of observations. The basic definition involves pairs. So the sample estimate is 1 over n choose 2, because there's n choose 2 pairs of data. And now we're summing over all s not equal to t, all distinct pairs of data, and we just take h of s minus h of t, y of s minus y of t, the sign of that, and we take that average. Yeah?
So do you count the difference between each pair twice?
I think I counted it. Did I count it twice? Or it doesn't matter. It's just a matter of whether you need a half in front or not. In other words, what he's saying is there's 2 ways I could write this. So I don't count them twice, or I do count them twice, and it's just a matter of dividing through by the right number of things. I think the way I've written it, you need to take all s not equal to t.
Don't we lose independence here?
Ah, excellent question. So something new is happening that's never happened before in the course. I'm dealing with an average. We've done a lot of averages in 705 and 702, 701, 715. Averages everywhere. This is an average, but the things that we're averaging are not independent. They're overlapping, right? Because now I'm taking all possible pairs. So first I take, say, this pair and this pair. Then I take this pair and this pair. Well, clearly, those are correlated because they both involved x1 and y1. So we've hit an interesting thing here, which is this is something, and I mentioned this briefly the other day. This is called a U statistic. Statistics of this form are averages of things which are not independent. And I mentioned the other day that the sample variance can actually be written. So if I just look at the sample variance, we usually write it like this. But it can also be rewritten, and I have to remember, is there a 2? There might be I might be off by a 2, but something like this, as the difference between all pairs. And this form is called the U statistic form. In general, a U statistic of order B means that you have some function, k of x1, x2, up to some number b, written in the following way. You sum over all possible subsets, x, let's call it s1. Whoops, it's okay. X sub. Okay, so in this case, it's a U statistic of order 2. This is a U statistic of order B. And U statistics are a generalization of the notion of an average. But instead of reaching in and grabbing one observation each time, you reach in and grab B observations, in this case 2 observations each time. And you keep doing that until you get all pairs and you average. It's still an average. It's still, if I take the expected value of this, I can still take the expected value on the inside. So it's easy to see that this is unbiased, because that's why it's called a U statistic, unbiased. It's an unbiased estimate of whatever it is it's estimating, kind of by definition. But all that theory we learned in 705, unfortunately, doesn't carry over so well because exactly what you said. These are dependent. So getting the limiting distribution, the variances and everything gets a lot more complicated in general. Yes?
How much efficiency can we gain from using the U statistic as opposed to, say, just getting that?
That's a great question, because that's going to get, remember I said that the one thing had the confidence interval, sort of. So you can use an n statistic, I just made it up, for non-u statistic. What I mean is you could block them into pairs like this. Just arbitrarily put them into pairs. And just use this pair, use this pair, use this pair. And now I'm back to having an ordinary average. The answer is you do lose efficiency. An order of magnitude of efficiency, I think. We'll talk more about that when I get to the distance correlation. And I've seen this. I did some work with a student who's since graduated about high-dimensional versions of these things, how to deal with correlations between vectors of very high dimension. And he compared the u-statistic version to the du-statistified, whatever you want to call it, the blocked version. And there really was a difference in the power. Yeah.
What's the name of the original statistic? It's called v-statistic or something else.
Sorry?
What's the name of the original one?
This one? Oh, well, that's just,
Have another name?
no. With sample variance. That's all. That's it.
Since I've seen many names like v-statistic.
V-statistic?
So what's that?
A v-statistic just means that you include the s equals to t terms. And it turns out they're asymptotically equivalent, but it's no longer unbiased. So some people prefer to work with the v-statistic version. Some people work with the u-statistic version. I think it's more common to use the u-statistic version. Yeah.
So, is this actually any more general as far as the strength?
Not yet. I haven't gotten to the stronger ones. No, it's not. If anything, it might be weaker.
Really?
It depends on the actually, I take that back. It depends on the it depends on the distribution. There are times when, so his question is, if I want to test for departures from independence, which one really has more power, rho or tau? And we didn't talk about this in 705, but there's a notion of efficiency, which is how much power do tests have against alternatives. Depending on the situation, depending on the distribution, there are certain situations when rho can have more power, and there are certain situations when tau can have more power. It depends on the distribution.
Is there like an intuition or exactly what that means? It seems like it's just monotonicity, right?
It's measuring a kind of monotonicity. That's right. It's kind of measuring a kind of monotonic type of correlation. Yeah. That's exactly right. Which is why when we get to the tau squared, you'll see we're going to try to generalize it to break away from the monotonicity.
There's no way you can construct two variables that are uncorrelated that are related in a monotonic way, right?
That are uncorrelated.
So it seems like they ought to detect exactly the same kind of dependence.
I didn't quite get the question.
So in theory, right, with the sample limit, right, in population, they detect exactly the same basis of dependence, right?
Yes. This is consistently estimating that population type of dependence. All right. So this is just, yeah.
How similar or different is Kendall's tau with Spearman's correlation?
Well, ask him, because he's working on a data set right now where the different types of correlation actually ended up being quite different. It really depends on the data. Yeah. So there's no general answer to that. They really are, in general, quite different. So, of course, there'll be some data sets where they come out to be very similar, but there will be data sets where they can be quite different. Okay, now how about the testing? It turns out this also has a very simple limiting null distribution in this particular case. I've written it down for you. It's just another normal distribution. So I won't go through it again, but I wrote it down here. You can just use the normal approximation to do a test or confidence interval. You can also do a permutation test to get an exact test and so on. So it's very similar to the Pearson correlation in that respect. There's not a lot different there. Okay.
Is the rate of convergence the asymptotic distribution variable also?
Yes. Okay. All right, but then for quite a while people have thought about, is there some simple measure of correlation? And you want it to be pretty simple in some sense. some statistic you can just compute from the data that will really tell you, are they independent or not? So in other words, a strong measure of correlation. And so I think a big breakthrough came in 2007 by this guy ZK, and I forget who the co-authors were. It's actually work he did years earlier, but somehow it never appeared till, I think, 2007. And then since then, there's been, as I say, kernelized versions of it, although I think the kernel people did it kind of independently, actually. So let me tell you the first version of this. It's called the distance correlation. It's going to look a bit strange, and I'll show you a few different versions of it. In fact, they have a whole paper devoted to giving several different definitions of this thing and showing they're all defining the same thing, just because the definition seems kind of not so intuitive. But here's how it works. We start with defining the distance. I'm going to define the distance covariance. Okay, and again, I'll just pick a pair of features. We're always going to do this, right, for every pair of features and then construct a graph. But let's just say we have two features. And the way I'm going to write it down, in fact, I'm going to allow these features to be, I've been talking about them being univariate, which is how we usually construct a graph. But these could even be vectors at this point. And here's the population definition. You imagine, again, taking two draws from the distribution. So it involves pairs again, actually more than pairs. And we take x minus x prime. So that's one draw, and that's a second independent draw from the distribution. And you look at the norm, or distance between those two things. And that's just a real number, right? Even though these might be vectors, this is just a number. Now we do the same thing for y minus y prime. We take the norm. These are just now two random variables. And you take the covariance between these. And that's not quite enough. Now we have to subtract off the covariance between x minus x prime. But now we have to introduce a third draw, believe it or not. So I'll call that y double prime. Okay, so what we've got here is, this is one draw from the distribution. This is a second draw. And this is a third draw. And what we're looking at is the distance between a typical pair of draws in the x space and a typical pair in the y space. And then there has to be some sort of correction factor, it turns out.
Should there be like x double prime?
No, believe it or not, it's not. I know it's very counterintuitive, isn't it? But I'm pretty sure that's correct. And it's...
So where does like x double prime appear in this equation?
It doesn't. We never use it. All right. Now we could do this we could also do this for putting x and x, and that would be called the distance variance. You know, the usual variance, except now it's this funny definition. And so the distance correlation, or actually the distance correlation squared, is defined to be this squared over the corresponding variance terms. So when you first see this definition, this is just some number. Doesn't seem that intuitive, I don't think. And it's between -1 and 1, it turns out. Okay. And here's the remarkable property. X and y are independent if and only if this is 0. So it does have the strong property, strong correlation property. Actually, yeah, that's right. Now, before I talk about how to estimate it, let me try to write down a couple more definitions. Because honestly, when I first saw it too, I thought, this is pretty weird. Why does this even work? And it is still a bit mysterious. It just does. But there are some other equivalent definitions that maybe make it seem a little bit clearer. So here's let me write it down and I'll explain what these terms are. I'm going to rewrite, the key thing here is the covariance, of course. Let me rewrite the covariance in a different way. There's constants. These constants, these are just numbers. They involve something to do with gamma functions. They're just literally numbers, so don't worry about those. The key thing is this. This can be rewritten in the following way. I'll define these things in a moment. Okay, so let me say what all this is. So what is for a random variable so one thing we've used a lot, especially when we did concentration of measure, was the moment generating function, right? But there's another function which is actually more fundamental, which is the characteristic function, which maybe you've seen before, or the Fourier transform, which is, it's just like the moment generating function, but you put I in here, where I is the square root of -1. So it's a complex thing, complex valued thing. It just turns out that's a more fundamental quantity. And roughly speaking, it completely characterizes the distribution. If you give me the distribution, I can compute this characteristic function. If they give you the characteristic function, you can sort of go back and get the distribution by inverting it. And so what this is saying, and by the way, it's easy to check by definition because of the E here, that if two random variables are independent, then the characteristic function is a product. So the characteristic function of x, y, ts would be the product of the characteristic functions. Just because, right, you'd have e to the I t y plus e y, I s y. The e of a sum becomes the product of the e's. They're independent. So the expected value of the product is the product of the expected value. So what we're measuring here is the joint characteristic function minus the product characteristic function. So that intuitively does seem like some measure of independence. And then to square it and integrate it. Now, I mentioned that x here could be a vector, so that's why there's a d. I'm allowing for the possibility that this is actually a vector instead of a scalar. If this is a scalar, this would just be 1. And that's it then. This is just the norm of s and the norm of t. So I think intuitively this seems like a reasonable candidate for measuring independence, because these two things are going to be equal if and only if the random variables are independent. And then we're integrating it just to get an overall measure of dependence. The remarkable thing is you never actually have to estimate the characteristic function. It turns out this is a theorem. It takes some analysis. It's identically equal to defining it this way, which is really surprising, I think. And the beauty of this is now you can see it. We're going to be able to estimate this from the data pretty easily. We're just going to compute all these distances and use a U statistic. Okay? But before we do that, I'm not going to do the proof that they're equivalent. If you want to see that, you can look at ZK's original paper. But it's certainly not obvious, right? They look very, very different. Okay, but let me write down one more way of writing this down, just because I want to try my best to make this seem somewhat intuitive. Oh, and by the way, let me make a side remark. Look at I have the norm of x minus x prime and the norm of y minus y prime. You could imagine replacing that with a more general kernel instead of a norm. Right? And you can do that. And there's a whole literature, especially in machine learning, about measuring independence, doing that. And those are called reproducing kernel Hilbert space measures of association. So you can either think of this as a special case of the reproducing kernel Hilbert space version, or you can think of the reproducing kernel as some sort of generalization of this, whatever you want. But they have the same flavor. Just replace norms with kernels. And the properties are very, very, very similar. I just picked this one because I think it's the first one, and it's the simplest one. But here's another way to write it down that may or may not help you. Let's try it. See if this feels a little bit more intuitive. It's the expected value of a new thing, which I'll call delta x and x prime times delta y and y prime. What's this delta thing? It's just a distance which has been sort of normalized to take off the if you think about the distances as a matrix, you can think of removing the column and row means. And this is what's going on here. This is some. So I'm writing d here now because d can be any distance. I've defined it above in terms of Euclidean distance, but actually any distance satisfying some weak regularity conditions, we could do the same thing, or a kernel, whatever you want to call it. But you can't just take the distances. This is why there's extra stuff here, is for this to have the property that we want, that it measures dependence, you need to do this kind of normalization where we take off, you can think of this as like the mean holding one variable fixed, and then the mean holding the other variable fixed, but by symmetry, and that's just taking two of those, plus the overall mean of this thing, which is. So maybe this is the most intuitive definition, is that I take the notion of a distance between two vectors, and I do some sort of normalization to it, just subtracting off a kind of mean type of thing. And so I'm just getting a modified notion of the distance between these two things, kind of removing the effect of the average distance between two things. Once I have that, it really is just the correlation between that for x and y. I should have mentioned that there's a paper, very nice paper by this guy Lyons in 2013, where he looks at the definition from this point of view and asks, what properties does this metric actually need to satisfy in order that the resulting measure of correlation really has the strong property? And he actually characterizes certain properties the metric has to have. But every metric you're going to think of is, well, not everyone, but most of the metrics you're going to think of will satisfy that property. So I'll typically be using the Euclidean metric. If you want to use some sort of kernel type of thing, that's fine.
So with this this definition here, so if delta were x minus x prime, so that would be the regular thing, right? No, the one above. If delta were x minus x prime, so that would become like the normal.
Yes, I'm just rewriting his definition a different way.
No, I mean, is it known like under what choice of t that would reduce
To the distance correlation?
to the normal correlation,
Pearson's correlation? It never reduces to Pearson's correlation. Because Pearson's correlation does not have the property, right, that it's zero if and only if it's independent. So it can't ever be Pearson's correlation. Well, yeah, I sympathize, but you can see that it's just that if I were trying to estimate these quantities, it's just like think of the Kendall's tau. You can see why intrinsically the definition requires pairs of data. And it just so happens that to measure these things, you need triples or quadruples sometimes of data. It's just what you need. I mean, I don't really have an intuitive explanation except that it comes out of the definition. In fact, because of the special nature of this one, so what we could do is try to take the original definition and take a U-statistic version of it. But because we can rewrite it as subtracting off some means and adding some means, there's an alternative way to compute it, which is the way that ZK actually computes it, and the way that it's done in the.
Why in the second definition there is no double cross?
Yeah, that's a good question. You know, I'm not sure why they can get away with it in the second definition. That's a little bit confusing to me too, and I've not figured that out. But I share the confusion. But it's just because to write it one way you only need x prime, and the other way you need x double prime. I'm not certain why, actually. But how people typically compute it is the following. So we form a matrix A where AJK equals. Now, I want to avoid some confusion. I'm still talking about two variables. I'm not talking about k features. I'm still only talking about two features. So the j and the k are not referring to different features. These are just the jth observation of x and the kth observation of x. Okay, so this is just a matrix of all the distances between the x variables. And we can do the same thing for the y's. So that will be b. And then it turns out you can write down an estimator of the form this involving all of these, just these matrices, the elements of the matrix. Oh, sorry. There's two different matrices. There's little a, that's supposed to be little a, and little b. Little a has these distances, little b. Big A has this normalization to it. So big A has the following entries. And here you're going to get some 1960s statistics notation. You take AJK, that's just the matrix of distances for the x's, and we subtract off AJ dot. There was a period of time in statistics where people love doing this. What this means is we've averaged over the column. So it's the jth column averaged over the row. A dot k means we've averaged over the column, and it's the kth row, or whatever I just said, maybe the other way around. So people used to use dots to mean if I take this matrix, I'm taking the individual entries and I'm subtracting this and this. And then I'm adding on the overall average, A dot dot, which is this. Just like in the sample variance, we could write the sample variance as this big U statistic, or xi minus an average, x bar. It's the same kind of thing. It's just algebraically a different way of writing this statistic. But it's really just estimating that thing. In fact, you can see it's closer. You can see this, right? It's like this. It's this minus the row sum minus the average sum plus the overall sum. That's really what this statistic is doing. And that's the sample version of that statistic. It's a pretty remarkable thing. And in fact, let me just say explicitly what the kernel versions of this look like. We're just going to put down the expected value of some kernel. Typically a Gaussian kernel. And times this. This is rewritten a slightly different way. Minus 2 times the expected value This is how you usually see it written in the kernel literature. But you can think of this as just a kernelized version of that statistic. There's a bunch of papers by Arthur Gretton and his colleagues that do this. One of the problems with the kernelized version, think of this as let's suppose this is like a normal kernel. There's a bandwidth to pick. There's no known method for how to pick the bandwidth. That is, nobody has any way that can be shown to have any sort of properties. So one of the problems with the kernelized methods is there's this parameter that nobody quite knows how to pick. And people usually use something called the median heuristic, where they look at all the pairs of the data points. They look at the distances. They take the median of those distances, and they use that as a bandwidth. It's called the median heuristic precisely because it's a heuristic, because there's no justification. The nice thing about the original version up there is there's no bandwidth to pick. There's no tuning parameters at all. It's one of the few non-parametric things where you don't have to pick a tuning parameter. It's kind of nice. All right. Yeah.
Does this generalize to a conditional measure?
We'll get to that. That's a really good question. Remember to ask me that when we get to non-parametric conditional stuff. Yeah. Right now, we're not doing any conditioning, right? We're just saying, is this vector x independent of this vector y? Or really, is this, when we're going to use it for graphs for now, it's just going to be, is this scalar x independent of this scalar y? In fact, how are we going to use this now to make a graph? Well, now we go back to the fact that really what we have are d features. And we're going to do exactly the same thing we just did with the Pearson or the Kendall's tau. For every pair of features, we're going to measure this guy. Say we'll get a test statistic and do, let's say, a hypothesis test. And say if they reject, we're going to connect them. Otherwise, we don't connect them. That would be one way of constructing a graph. And this is a non-parametric dependence graph now.
Is this computationally feasible at all?
Sure. Yeah. I mean, that's not that hard. You just do it for all d choose 2 pairs. Compared to the things that people are doing for like deep learning and stuff, right? This is a blink of an eye. However, there is a catch. How do I get the critical value for the cutoff? Well, I could do a permutation test. Now it is getting expensive, but it's still doable. Okay? Or maybe I could ask, what's the limiting distribution under the null hypothesis, like I did for, say, the Pearson thing? Now we run into a problem. Because we can re-express all this thing as some sort of very now complicated U statistic, but it has a property called, it's called a degenerate U statistic. It's a certain type of U statistic. So I forgot to mention this here, but let me say what the property is. If I look at gamma hat squared under the null hypothesis, say the null hypothesis, it turns out, first of all, it doesn't converge at a square root n rate. It converges at an n rate. It has to be multiplied by n. But it doesn't converge to a normal. It converges in distribution to something that's called a Gaussian chaos. What the heck is that? And the name is appropriate because it's pretty wild. All right? It looks like this. It's converging to a distribution which is a sum of infinitely many things. These are constants. These are numbers that depend on the underlying distribution. So in other words, there's parameters in the limiting distribution, and we don't know them. These are chi-squared distributions. So what's happening is you're getting it converges to the limiting distribution is an infinite sum of chi-squared distributions with a bunch of unknown parameters in it. So the bad news is there's an interesting trade-off here. What we've gained here is a true test of independence. True non-parametric test, are these two features independent? We have a terrible price to pay, that the limiting distribution, if we wanted to do a test, this is a useless limiting distribution. You can't use a null distribution which has infinitely many unknown parameters in it, right? That's not. Then there was some papers where people tried to estimate this. You don't want to do that. That's not the right way to do it. Now there is an easy solution. Permutation test. Expensive, but it works. Okay, how about the confidence interval, though? That one's very tough. And the only solution I know right now is what was suggested earlier, which is I didn't write this as a complicated U statistic, but you can rewrite this as a U statistic of order 4 or 5 or something. I forget what it is. But whatever it is, we can rewrite this as a U statistic, and then you can do the block version. So instead of, let's suppose it's a U statistic of order 4. So I could rewrite this as a sum over all subsets of size 4, let's say. The alternative is to form blocks. of size 4. So I take 4 observations. I compute the thing that goes in the sum once. That gives me a number. That's a single number. Now, I take those 4 things, I compute that number, and I repeat this. So the difference between this and a U statistic is a U statistic I'm taking all, I would take all n choose 4 subsets of size 4. Here, I'm just breaking it into blocks of size 4. I'm not using all of them. The advantage of this is when I do this, all I have now is an average of independent observations. And sure enough, you can just use the central limit theorem. It's just a normal. You can use the usual z statistic to do the test, and you can construct a confidence interval. That's one way to get the confidence interval. The problem with it is inefficient, which means that the test, for example, has lower power than it should have. The full test, which uses the correct statistic, has higher power than this blockwise thing. And I'm pretty sure it's also true that the confidence interval is longer than it needs to be. So there's an interesting problem with this distance correlation and all the kernelized correlations, which is that if you form the block version, you give up efficiency, statistical efficiency. You actually gain computational efficiency, right? That's much faster. And you gain the ability to construct a confidence interval. But you lose statistical efficiency. Very interesting phenomenon. I don't know of any way yet that uses all the data, that uses the full U statistic and constructs a correct confidence interval. I haven't seen. So that's another problem. And you really do lose power. Like I say, I had a student who did some of this in his thesis, and he both theoretically and through simulations compared the blocked version to the U statistic version. There's no doubt that the U statistic version has much power than the blocked version. So that one's, this is, I'm trying to bring you here to the cutting edge of knowledge, because I think the fact that people have come up with simple ways to test complete independence is really interesting, but the problem isn't completely solved yet, at least if we want to get confidence intervals. How are we doing on time? Okay. Want to make sure I haven't lost you yet. I know I'm throwing a lot of stuff at you, but we just have now, so far, a statistic for any pair of features. We do a test, say, do it for every pair of features, and we get a graph. We'll see some examples in a few minutes. Yeah, hang on to the conditional independence questions, which are very interesting.
Does the function in the U statistic have to be symmetric in all its arguments?
Yes, I should have said that. The way a U statistic is defined is that that function is symmetric in its arguments. If it isn't, usually people symmetrize it. You just take the average over all permutations. But everything I've talked about in terms of the theory assumes it's a symmetric function of its arguments. Yeah, U statistics are really interesting things. They have a lot of different properties than the usual statistics we're used to. And it's another interesting example of where it was this part of statistics that some people worked on. And then in the last 5 years, it's become part of machine learning, largely because of these things, and also some 2 sample tests turned out to be U statistics. And so now there's actually quite a few NIPS papers and so on about U statistics. It's very interesting. It's become it's moved from statistics into machine learning. It's very interesting. All right. So I lost my beautiful chart, but we've done 3 of the 4. I can at least start the 4th one, which is extremely new. As far as I know, this was invented in 2014. And it's basically combining Kendall's tau with the distance covariance. Okay, and it's from 2 guys named, I don't know if I'm going to say the names right, but Bergsma and Dacios. Okay, so if you want to see the paper, you just Google Bergsma and Dacios. They call it the tau star correlation. And they had what I think is a really, really brilliant insight into why doesn't Kendall's tau actually measure full correlation. And it comes down to the notion of concordance. So what's going to happen here is there's 2 ways to view this statistic. I think this is really interesting. One way is it's going to turn out to be a version of the distance correlation where covariances and everything, where we put a sign in front of everything. I'll show you in a minute. We're going to put signs in front of things to make it like a tau, Kendall's tau-like thing. But a different way is a geometric thing. So here's the here's the idea. And as far as I know, there's only been about 2 papers on this so far. So this is very new. Not a lot is known about it. But its basic property is that it's a strong correlation. So let me first of all just write down the definition. It's defined, again, I'll just take 2 features and call them x and y. And it's the expected value of, here we go, A of x1, x2, x3, x4, B, y1, y2. So you can see we're definitely in. Well, that's correct. It's A. What matters is that these are y's and these are x's. The function A is fixed. So this is a 4th order U statistic, right? This is a function of 4 variables at a time, a 4th order U statistic. What is A? I see there's a typo in it. It's A of z1, let's say z2. It takes 4 values and outputs a real number. And it's z1 minus z2 plus z3 minus z4 minus, and there's an absolute value missing here, z1 minus z3, this is missing in the notes, minus z2 minus z4. But it's the sign of this thing. Okay, now here is the very, very cool thing. And you might wonder, how in the world would they think of this? And look at all the differences. They're taking sums and differences of differences. If I didn't have the sign here, it turns out you'd get back the distance correlation. So they found a new way to rewrite the distance correlation. But then the cool thing is just by putting a sign in front of it, they get something more like a Kendall's tau, which is very robust to outliers. See, that distance correlation, because it involves those norms between vectors, if there's an outlier in there, that can be, one of those things could be huge. By putting the sign here, it becomes very robust. But they've proved that this thing still has the strong property. This is 0 if and only if x is independent of y. Very cool. This is one of my favorite things in the last couple of years. And there's a geometric picture of what's going on. How are we doing for time? All right. They have, and I don't know whether they thought of this first or thought of this geometric interpretation that's at the bottom of page 6, which is just to redefine what you mean by concordant and discordant in the Kendall's tau, which is, roughly speaking, here's the picture you should have in your mind. So we're going to do this with the data. It's going to be just a 4th order U statistic. I'm going to compute this for every quadruple of data points and average. But imagine taking 4 points at random from the data and looking at them. What they're looking at is they're saying which ones look like a dependent sample and which ones look like an independent sample. And what they're calling discordant or independent is this. This looks like an independent sample. This looks like there's no dependence, right? When they're in different quadrants like that. They're going to call anything that lines up like this concordant, anytime they fall in quadrants like this. These sort of suggest dependence, and this suggests independence. This is concordance, discordance. Instead of a 2-point notion of discordance, concordance like Kendall's tau, it's a 4-point notion. 4 turns out to be just enough because they proved that you can write tau square is nothing other than, if we define it this way, you can prove that this is equal to 2 times the probability that they're, let's say, concordant, that is, that they fall in a configuration like this, minus the probability that they're discordant. And there's some constants here, over 3. So intuitively what they're doing is they're just looking at quadruples of data and saying, well, these suggest dependence, independence, this suggests dependence. We compare how many there are. That's going to be our measure of dependence. And it works.
What does this picture mean? Could you explain it?
What does this picture mean? I mean, I've drawn 4 points. I just draw 4 points, and this is the 2 axes. Let's say I've subtracted off the mean, and I'm just seeing do they fall in 4 separate quadrants or not.
There's sample points.
These are just 4 randomly drawn sample points, right? Now, that's right, yeah. And then
What is contour probability in this graph?
it's just how many, every time you draw 4 points, you say how often do you get a configuration like this? Well, yeah, that's not so easy to see from here. There's a bit of analysis to do to show that those two things are the same. Yeah.
What about the other case, if we, for example, if we have three quality inverse,
Right, we're not worrying about those. That's not part of the definition. So this turns out to be, so that the real definition's over here. And then they have a theorem that says it's really just counting those. And how do we know those are the right ones to count? Well, they're right in the sense that it gives us a strong correlation, provably. And the sample version is just the sum over all n choose 4 pairs of A applied to those 4 data points. So here's 4 x's, here's 4 y's, and you do it over all n choose 4 pairs. Very cool. I think this is really, really interesting. So we've run out of time. Tuesday, I'm sorry I went over even. Got a little bit too excited about tau star. We'll finish this up, then we'll do partial correlation and then conditional independence. And that'll be on Tuesday. All right.